Okay, electric circuits, the EMF of a battery. Well, the mark scheme answer is this: it's the work done per unit charge, moving a charge completely around the circuit. And what's electrical resistance? Well, electrical resistance is V over I, but we need to state that in words. That's the ratio of the voltage to the current in the conductor. Now, we need to write an equation, state an equation giving the total power delivered by the battery in the circuit. Well, power is voltage times current, so it's simply the EMF times the current. And then, using the fact that we know V1 and V2, what can we write down? Well, the total energy of the total power output by the battery is, again, the EMF times the current. And that energy must be dissipated either in the first resistor or in the second resistor. The sum of the energies dissipated must equal the output of the battery because of the conservation of energy. So EMF times I must be equal to the energy dissipated here, so that's going to be V1 times I, plus the energy dissipated in the second one, which would be V2 times I. And the i's cancel, and we get this rather obvious answer. Now, we have a graph showing the IV characteristics of two conductors, and we want to sketch a graph of how the resistance of these two conductors varies. Now, remember that resistance is voltage over current, so we can read it off this graph as the voltage divided by the current, which, by the way, is not quite the same as the gradient. Well, it's not the gradient. The gradient is the rate of change of one with the other. So it's not the gradient, it's the actual absolute value of one divided by the other. Looking at x, well, it doesn't matter what value you take here. Do you take 1 over 0.2 or 2 over 0.4, 3 over 0.6? Because it's a straight line through the origin, it's proportional, the ratio doesn't change. So the resistance of x is a constant. So we can represent that on this graph by a horizontal line and label that x. Now, how does y change? Well, y, we can see y starts off steeper. It starts off with a larger current for the same voltage. So if we have a larger current for the same voltage, that means it has a smaller resistance. So y starts off with a small but non-zero resistance. But over time, the current doesn't increase so much with the voltage. And we get to a point here where you get the same current for the same voltage. Both of them give you 0.8 amps for 4 volts. So at this point, the resistance of Y must be equal to the resistance of X. And then after this point, well, I doesn't go up much. V keeps going up, but I doesn't go up. So the resistance must be higher for Y at this point. So it's not obvious whether, just by looking at the shape here, whether the resistance increases as a straight line or as a curve. It doesn't matter how we draw it. So I'll just give the simplest answer, which is a straight line. But a curve would be, a curve that follows the same pattern would be equally acceptable. Now part D, we have those two conductors that were shown in the previous graph, X and Y, connected in a circuit. And first we need to use the graph to determine the EMF of the battery. Now, if the two conductors are connected in series, one thing we can say is that the current passing through X must equal the current passing through Y. And the question also tells us that the power dissipated in each of the two resistors is the same. Now, the power dissipated in a resistor is VI. So, if the current in both resistors is the same, which it must be, and the power dissipated in the resistors is the same, then it follows that V, the potential difference across each resistor, must be the same. So if V and I are the same for both resistors, there's only one possible value of that V and I, and that's this point where, well, actually there's two, there's the one down here, but the one with the non-zero value is 4 volts and 0.8 amps. So there must be 4 volts across X and 4 volts across Y. And so very simply, the EMF must be 4 plus 4 is 8 volts. And the total power dissipated in the circuit, well, power is V times I. The total power is going to be the 8 volts times the current flowing in the circuit. Well, the current flowing through both resistors, we read off the graph, was 0.8. So that's 6.4 watts. Now, energy balance of the Earth. First, it tells us the intensity of the sun's radiation at the position of the Earth is this much. So why is it that the average power received per unit of the area is only 350 watts per square metre? Well, the answer to this is the fact that the Earth is round. So some light hits directly at the equator, which is directly facing the sun, and that will have this higher intensity, 1400 watts per square metre. But when we talk about the average power received per unit area of the Earth, we need to average over the whole surface area of the entire Earth. So we need to explain that. And the mark scheme answer is asking for this. First we say that the solar radiation, or the instant solar radiation, is basically the radiation that is instant on the disk. If the Earth were replaced by a flat disk of area pi r squared, but this is averaged over the entire surface of the Earth, which is 4 pi r squared. Now here we have a model of the energy balance of the Earth's surface. And first we want to state the emissivity of the atmosphere. So what's the atmosphere doing in this diagram? Well, the atmosphere is radiating energy down towards the Earth's surface. And we know that the power radiated by something is, if it's not a perfect black body, is the emissivity times sigma A T to the 4. So comparing that equation to what's given here, we can see this 0.7 represents the emissivity. Now we need to show the intensity of the radiation radiated by the atmosphere. Well, the intensity is given by this equation. The temperature of the atmosphere is also given, so we just put this number in this equation. Emissivity times sigma times T to the 4th. Stefan Boltzmann constant, 5.67 times 10 to the minus 8. That's from the data booklet. And we work it out. And finally, we need to calculate TE, the temperature of the Earth. So if we look at what the Earth is doing, well, the Earth is absorbing energy from two sources. It's absorbing energy that's transmitted directly through the atmosphere, that's 245 watts per square metre, and it's absorbing energy that's radiated by the atmosphere, and we just calculated that that is 136. The total energy received, or the total intensity received, is the 245 plus 136. Now, because the Earth is in thermal equilibrium, the intensity received must be equal to the intensity emitted. So this is also the intensity being emitted by the Earth. Let's add them together. And we know the equation for the intensity being emitted by the Earth. That is emissivity sigma TE to the fourth. And if we assume that the emissivity of the Earth is 1, that is, it is a perfect black body, we just ignore the emissivity, and we plug the numbers in and calculate the temperature of the Earth. The TE to the fourth will be 3.81 over sigma. So take this fourth root of that, and we get TE is 286 Kelvin, a nice comfortable temperature. Now, the mechanism by which part of the radiation radiated by the Earth's surface is absorbed. Well, the first point here is that because of the temperature of the Earth is around 286 Kelvin, the part of the electromagnetic spectrum that the Earth is radiating in is the infrared region. So it's infrared radiation is emitted by the Earth. And that's key because as the radiation travels through the atmosphere, it encounters greenhouse gases. And the thing about greenhouse gases is that their bonds resonate at these frequencies. So greenhouse gas, or let's say greenhouse gas molecules, resonate at frequencies corresponding to infrared radiation, let's say at infrared frequencies. So why is that? Why does that absorb energy? Well, they resonate. No, so photons are absorbed. And that answers the question. And if we want to explain why this makes the Earth warmer, then we need to go on to say that the energy is re-radiated by the greenhouse gases, and half of the re-radiation is down back towards the surface of the Earth, so the Earth reabsorbs that energy and becomes warmer. But why is incoming solar radiation not affected by this mechanism? Well, how is incoming solar radiation different? It's not infrared radiation, it's in the UV region. And the UV region has different frequencies that are not absorbed by greenhouse gases or any other gases in the atmospheres. Carbon dioxide is a greenhouse gas. You need to state one source and one sink of this gas. The source, where does this come from? Why is there lots of it in the atmosphere? There are lots of possible sources. Most controversial one is the fact that we burn fossil fuels. By the way, it's not enough just to say fossil fuels. We need to say what we do with them. We burn them. But I'd be tempted to write down the most obvious one, something I do every minute of every day, which is just breathing. And a sink is something that absorbs CO2 from the atmosphere. There are many of them: oceans, trees, plants.